Hello, everyone. My name is Muhammad Jahanzaib Naveed, and I'm going to be talking about my thesis titled Optimized Code Generation in BIM with Retrieval Augmented Large Learning Models. This thesis was done in collaboration with Trimble, Finland. Yeah. So first, I'm going to be going over introduction of some basic terms. Afterwards, I'm going to be going over the background and aims of my thesis. I'm going to be explaining my experimental setup, followed by the methodology, and then finally, I'm going to be concluding with the results and conclusions of my thesis. So building information modeling, or BIM, is a type of software used in the construction industry to basically make digital representations of architectural projects. So for example, if you want to make a building, if you want to make any sort of infrastructure, you can design it in BIM software. Large learning models, as everyone knows, are artificial intelligence models designed to understand and generate human language. And for example, ChatGPT, they're trained on vast amounts of data, and essentially they can produce human readable text. Integration of LLMs into BIM has huge potential because it can increase the productivity of the software. It can make the software easier to use, easier to understand, and essentially you could use the LLMs to do actual functions within the software, which can dramatically just increase user experience and make the software better. So most LLMs like ChatGPT, they're general purpose assistants, meaning they're not very, so if you want to ask it something very specific or very niche, it might not be a very good tool. One way to circumvent this is to retrain the model, but then this can prove very expensive. So another technique is retrieval augmented generation, or RAG simply. And then what RAG does is that it creates a separate knowledge base which the LLM can use. And then essentially you can ask the LLM a question, it would retrieve relevant documents from the knowledge base and then use its own training data and the knowledge base to generate responses, which would then be more accurate if regarding specific topics and stuff. So some background. So integration of LLM into BIM software has been slow recently, and there haven't been a lot of very major developments. Most of them have been limited to, for example, using diffusion models to make sketches and stuff. Otherwise, some BIM models allow limited functionality in their software using LLM. So you could ask the LLM to make you a beam, and it might be able to do so, but then it's still just that one functionality is very limited. It's not general purpose, and so that is also missing currently. One way to circumvent this, of course, is to use RAG, which could then allow the LLM to then perform actual software functions within the software. So you could tell the software to make you a beam, and then it would make you a beam within the. You could use LLM to make you a beam, and it would make a beam within the BIM software. But then there's been just limited research on how well these RAG-enabled LLMs work in these BIM software, and then there's no conclusive benchmarks to measure how well they actually perform. This is where sort of then my thesis comes in, where first we investigate the effectiveness of RAG-enabled LLMs in a BIM context, see how viable they are, and if they could present a good solution. And then finally, also evaluate the performance of various RAG models. So for example, because there's various ways to implement RAG, we are going to then have those various implementations, and then also have some sort of baseline through which we can then compare all these models and find the most effective ones. So some are set up. So for my thesis, I've used Tekla Structures, which is a popular BIM software owned by Trimble for creating and managing 3D software. We also use Tekla Open API, which is an API created by Trimble to create custom applications in Tekla Structures using the .NET framework or C#. Uh, so essentially, you would then you can create code files or macros as they're called, and then through the macro be able to then like run those files within Tekla structures. And those code files could be, for example, making a beam or making different templates within the software, and the software would be able to do that, and the API would allow you to do that. And then finally, we're going to be using the Tekla Developer Assistant. So this is essentially the LLM that we're going to be working with, which is going to take user input and then essentially generate the code files necessary to make all the functionality happen within Tekla structures. So some more information about the Tekla Developer Assistant. Essentially, it is a GPT like any other. It would take user input, and then it would give you a response. The knowledge base that we use over here, that's made by a Tekla Open API. So for example, we looked at the documentation for Tekla Open API, we parsed through that documentation, and then we made an index, which then sort of served as the knowledge base. The GPT models that we've used so throughout this thesis, we've used two GPT models, the GPT 4.0 and 4.0 mini, both owned by OpenAI. And then we also then change the temperature. So the temperature just sort of determines how random the GPT response will be. Lower temperatures means low randomness, high temperature means high randomness. And for our thesis, we have used two sort of temperatures for this experiment. So these are then the actual RAG models we've utilized. So one is keyword extraction, where essentially you take the user prompt and then you use an LLM to retrieve keywords from that prompt, and then use each of those keywords to retrieve documents, and then you tie them all together, and then you use them to generate your responses. The other RAG models are, for example, multi-query, where you rephrase the user prompt from different perspectives, and then from each of those different perspectives, you retrieve documents, and then you sort of combine all those documents together to use for your response. Logical routing is a bit more interesting, where for example, use the LLM to predict namespaces relevant to the user prompt, and then once we retrieve those relevant namespaces, we retrieve the documents for those namespaces, and then use them within for our response. And then finally, no rag is essentially the idea is that we would be using no rag or no external knowledge base, and then we'd just be relying on the pre-trained knowledge of the GPT. And this would essentially act as a benchmark to understand how well rag sort of improves the performance compared to just using the pre-trained knowledge of the GPT. So for our data and model, essentially we created a list of 100 prompts to be tested. So, and these prompts were prepared from various sources like interviews, forums, interviews with developers and users, etc. And then basically these prompts tested different functionalities in Tekla structures. And then so we would send the prompt to the assistant, and then ask the assistant to create a code file or basically a macro, and then we would run that macro in Tekla structures. If the macro was passing without any errors, then it would be context passing. If it was failing, then we would actually reprompt it. So reprompting is also, I think we sort of experimented where we would then we would ask the GPT to sort of correct its errors by sending the error message and then asking it to generate a code file again, a macro again, and then rerunning it. And then we did this a maximum of 2 times. And just the idea was to let the GPT be able to correct its mistakes. And then if it was passing, great. If it was not, then it would be marked as failing, and so on and so forth. And for this thesis, the RAG implemented tested would be then compared against a common loss function, which we'll explain later. And the selection of which LLM model to use, so GPT 4.0, 4.0 mini, and the temperature can be considered the hyperparameters for these models. And then the impact of these hyperparameters is then also compared as well. We utilized a binary loss function to compare the results of each of these RAG models. So if a prompt passed, it would have a value of 1. If it failed, it would have a value of 0. And the idea was is that a good model will have a low loss function with the fewest number of reprompts. So these are then the results. And over here, we can see the results of our RAG model. So this is all the 4 models that we've tested. From our experiments, we found logical routing to be the best model since it gives the best score from when it produces the original macro, and then after the first and second reprompts, it sort of gives the best value as well. And then we can also see that for all the models, the performance increases significantly after each reprompt. So reprompting does improve performance quite a bit. And then comparing all these models to the no RAG model, we can see that having a RAG, having a external knowledge base does significantly improve performance compared to just like not having it. Um, yeah. Yeah. And then over here, you can see the um, results of the hyperparameters. I won't go into too much details about the results, but then overall, it can be seen that lower temperatures generally improve performance compared to higher temperatures. And the choice of GPT, whether that's 4.0 or 4.0 mini, has a lower impact, and it doesn't really affect affect the performance of models that much. So for conclusions, so we can conclude that RAG models do provide a reliable enough code, especially given a sufficient number of reprompts. They reached a like logical routing reached a score of 0.118, which means roughly 80% of the code passed after 2 reprompts, which is a sufficient number, but of course that could be improved. And then reprompting can significantly improve the performance of RAG models as well. Logical routing seems to be the best model we've tested so far, and lower temperatures usually mean better performance. For our future work, it could be followed that we test even more RAG models under a wider variety of hyperparameters, and then we then investigate the actual output of the generated files as well. So instead of just checking for compilability and execution like we did now, we can actually go into these like files as well and see what they're producing, how well they perform, and then if they're actually producing code the way that we want, producing objects the way that we want them to. A final thing would be just having having a cost analysis of these RAG models as well, just seeing how much they cost, how much they work, and how much they would cost in a more production environment, which would then allow us to have a better idea about the feasibility of each of these models. But that concludes my presentation. Thank you for your time, and I wish you a pleasant day.